want to go in quarantine.
At the same time, I think I'd really hate it. I wouldn't get anything done if I went virtual.
It's dangerous.
I wouldn't do.
You need to have a lot of self-discipline because you don't got teachers telling you what to do. You don't have a class.
At my own house is the problem. So like over the summer when we went virtual, I was at my uncle's house doing all my schoolwork because I was at the farm. I was working the whole time.
Okay.
So when I was just over there the whole time, so I wasn't as distracted versus when I'm up in my room and I see something I'm like, oh yeah.
Yeah, or you find a rabbit hole on YouTube.
Yeah, at least
something.
when I'm at school, there's an adult who's keeping an eye on me.
Right, but really that is a real problem that when kids go virtual, that they can't hold themselves accountable. They don't manage their time. They don't.
Why I'm here.
Or
have
motivation.
Yeah, or they don't have the motivation, which. Again, that's what you agree to when you do school virtually is, hey, I'm responsible for my work and for checking my email and checking classroom, and yet kids, they can't handle that, at least some of them. So, yeah, think twice if you're wanting to go virtual next semester. I hope none of you do, because I'd rather you be here with me, but...
Well, it's also harder because you can't exactly ask questions very quick. There's delay.
Yep.
Because you answered pretty quick, but it's different from. So if I have a question, then I have to switch over to something else in the meantime. And I can't. I don't know how quick you can respond. Because some teachers you did it fairly quickly, but some teacher last year I emailed her and then it was 16 hours later got a response oh that's great.
Well, and to be fair. Any sort of expectation for an email reply is within a business day, right? That if you don't hear back within a day, that's their mistake. They should have replied sooner, and you can follow up. But you're right. If you're doing homework and you got a question, there's no way I could email back within even 20 minutes. That's crazy.
It wasn't even during a busy time. It was in the middle of the day, and it was technically supposed to be during the hours or whatever of the.
Well, yeah, that's
day.
true.
So
right?
It wasn't it was 8 o'clock at night. I was I understand late in the evening. I wouldn't send email, but normal hours of the day, I feel like.
True. If you emailed me during a work during the school day, I should get back quickly. But you're right. In the evening, I might put my computer away for the evening, and I'm not going to work at 7, 8 o'clock. I checked my computer once this weekend, which is insane for me. Checked it one time Saturday morning, and that's it.
I don't look at my computer. The only time my computer's out is at school.
Okay, so let's get started. I don't want to. Today is all review. That's all I got for you. So that means I need you guys to tell me how I can make this useful. One thing that I definitely want to do is remember the big ideas or the key concepts document on Classroom. I want to go through and talk about all those key concepts for Chapter 5 or Unit 5 Momentum. That's one thing I'm going to do for sure. We can talk about the homework if you want. Otherwise, I want to start with, questions. Does anybody have any questions about the homework? Think big picture for this test. Mr. H, I don't get impulse. What the heck is that? Let's go over that again. Yes. For real?
Yeah.
Okay, yeah. I need to know. Let's think about. Let's make a list of, impulse. That's something you guys want to review? Make sure everyone can see that. Oh, yeah, they can see that. All right, so impulse. What else? Aiden?
I got 2 questions.
Homework questions? Okay.
Good job.
I'm gonna put you. What else do we got? We talked about momentum equation. We talked about the change in momentum, which is related to impulse. We had conservation of momentum, right? When you look at a system, how is momentum conserved? How you define your system. We still got to learn, we got to know open system, closed system. That changes the answer to a lot of questions. Collisions. questions about collisions, right? Elastic versus inelastic. Finding your system in the collision.
Can we do something about like the one with the like stop with bullet and like?
Oh, like the pendulum?
Yeah, like the pendulum question.
Okay. Yeah, that's a classic.
Shooting ball.
It's a good one. Collisions, conservation momentum, they're tied together.
No, I'm assuming the test is going to be formatted similar to the other tests. So there's questions about concepts and multiple choice and free response. Or not free response, but like ones where you have to like
do math.
Yeah.
Yeah, I'll try to blend them all. Like, have some true-false conceptual questions, maybe some definitions of key terms or key equations. But then the majority of them are going to be, like workout problems. What is the initial momentum of this system? What's the average force applied during this collision given a momentum change? You got a certain collision. What's the final velocity of this cart? Right? So I'll hit all the main topics, but the majority of the test is going to be workout problems. Right? Use conservation of momentum to tell me the final velocity of cart 2 after an elastic collision. Stuff like that.
Throw some collisions on there.
Huh?
Throw some collisions on there.
Collisions? Oh yeah.
Do elastic collisions more?
Collisions?
Yeah, elastic collisions.
Yeah, if we can focus on
How
elastic
do
collisions.
them, and what's the difference?
I feel like inelastic is. I say this now.
I feel like I understand inelastic a lot better.
The sticking. Okay.
Yeah.
Any other key topics we want to add to our list? We good with that? This is helpful. This allows me to focus in on the things you really need help on so that we can, make this time valuable. I guess I'll go right down the list. Impulse. What's the letter, the variable letter that we use?
It's a little Roman P.
Impulse.
No, that's momentum.
That's momentum.
It's J.
Is J. Impulse equals
capital J, right?
capital J, right? This isn't to be confused with the unit of energy, joules. You use a capital J for the unit of joules as well, but that's after a number, right? You would always say like 15 capital J. That means 15 joules. If you ever have J by itself, you're talking about the impulse, right? Does anybody know the equation for what impulse equals?
Force times time.
Yes.
For the change in time, sorry.
Yes. I always do delta T. A force applied over a certain amount of time is what an impulse is. That is the definition. Not only via the equation, but also the equation tells you the conceptual definition. It's a force that acts over a certain amount of time. Specifically, sometimes AP will probably try to trick you on this. This technically is force average.
Listen, AP, you don't need to
It's really weird because in reality, like say I'm pushing a wagon. I push it with a certain amount of force for a certain amount of time. Am I pushing exactly 5 newtons every single millisecond throughout that? In reality, no. You would actually plot a graph. It would, maybe it spikes at the beginning, levels out, and then drops off at the end. You would actually take, again, this is where the calculus would come into play to get the exact answer. You would take the area under the curve for force over time, F times T. That would be your total impulse. For algebra based, this is your algebra version of that equation. You average out the force for the entire time period that you're applying, right? The whole time that I'm pushing on, say, the wagon. You want to calculate an average for that amount of time, then multiply it by how long you applied that force. That's what impulse is. So I only bring that up because sometimes AP will say, hey, what was the average force applied during this collision? You're like, average force? How do I get an average? What they're meaning is this F in the impulse equation. That F is implied as an average because, again, algebra-based, we can't tell for sure. Okay? So impulse is capital J. The impulse is when you apply a force for a certain amount of time on an object. What is impulse also equal to? Good. Delta P.
Lowercase little Greek p thing.
Yeah, you could do the rho. Again, that's not universal. Not everyone will do that. The safest variable would be a lowercase p. But I've always done rho. It can sometimes get confused with density, which often uses rho. But regardless, a p or rho, whatever. The change in momentum is what the impulse is. Right? This is how an object gets more momentum or loses its momentum. For an object to change its momentum, the only way that is possible is if you apply an impulse onto that object or system. Right? You have to have a certain force act over a certain amount of time on the object to be even possible to change its momentum. Otherwise, momentum will be conserved. Right? Again, this is going to be a tricky thing. The change in the momentum is the impulse. The impulse does not equal the momentum. Right? You hear the difference in what I'm saying? J equals delta P. Right? It has no bearing on the actual momentum. All it tells you is from start, you could rewrite this as P final minus P initial. The change, the difference from starting to ending is what J is. Alright? So if I have force of 50 newtons applied for 0.5 seconds, tell me what is the change in momentum?
It's 25. I don't know what's the unit for that.
Good question.
Like Newton seconds?
Would Newton seconds work? So Ethan, you said 25 Newton seconds. Does units make sense? Yeah.
Well, wait.
Force times time. Force is in newtons. Times in seconds. Newtons times seconds. Newton seconds works. Right? You could also write this unit is exactly the same as this one.
Fancy.
Remember, two ways to think about it. A newton is a kilogram meter per second squared. If I multiply by a second, I eliminate 1 second from the top and the bottom. So all I'm left with is kilogram meter per second. That works. You could also see, hey, the impulse is equal to the change in momentum. I know momentum is kilogram meter per second. So those units better match up if impulse is equal to the change in momentum. Both ways you can think about it. So Newton seconds or kilogram meter per second, same thing. Both are acceptable and true. Okay? Again, this doesn't tell us anything about momentum initial or momentum final. The only information we can determine regarding momentum is how it changed. I don't know the starting or the ending. A problem might ask you, they might give you this and say PI equals 18 kilogram meter per second. And the whole question is trying to find P final. So you'd have to first realize, okay, my impulse could tell me how the momentum changed. It increased by 25 because I got a positive number here. It's another key thing. If I had a positive change, that means, right, delta P is P final minus P initial. The change was 25. I don't know the final, but I knew the initial.
Add.
What?
Said add.
Add, yes. Add 18 to both sides. Just your basic algebra. 30, 43, right? They might want this, and you got to go through a couple steps to get there. Don't make the mistake of saying, oh, the final momentum was 25, because that's what the impulse equals. No. Impulse is the change. Okay? I'm stressing that because AP will try to take advantage of that common misconception. They want to test if you actually know what we're doing. Right? That'll be a common mistake that they're going to try and test. Like, hey, are you going to make this common mistake, or do you actually know what's up? Do we feel okay about impulse? Another thing to remember, you could apply a negative force and get a negative impulse. What would a negative impulse do to your momentum?
Be acting in the opposite direction.
Huh?
It'd be acting in the opposite direction.
Okay, yes. Your impulse would be opposing your motion. Well, actually, you don't know that for sure. Because you could start with negative momentum, have a negative impulse that gives you more negative momentum. No. No, you can't determine if the object changed directions unless you have an initial momentum that was, say, positive and a final that was negative. If you have your starting and ending momentums that are opposite signs, that means you change direction. Because your momentum is mass times velocity. Well, your mass is a number. That doesn't have any direction, so the only thing would then be your velocity. If you have a negative momentum, a negative impulse, but you started with a positive momentum, you would lose momentum. You would do your math. Your math would tell you the answer. But say this was a negative 50. We would get negative 25. Negative 25 plus 18 gives us, what, 7?
Yeah.
Oh, yes, thank you, Meg. Negative 7. So in that situation, Aiden, you would have negative 7 kilogram meter per second at the end, and you would have started with positive 18. So in that situation, you would have changed direction. You don't know that for sure unless you actually do the math and keep track of your signs. Trust your math, right? You know this. Let it tell you, is it positive or negative? If it's negative, I flip the other direction. Okay? But the basics. Impulse is J. It's the average force times the time that force was applied. It creates a change in the momentum. That change is P final minus P initial. Calculate all those, plug them in where you need them. The only way your system could change momentum is if an impulse happens. It's the same thing as a force, right? You got an object in motion, that thing will never, ever stop unless a force acts on it. In momentum, you will never change your momentum unless some force acts for a certain amount of time on that object. Otherwise, nothing's going to stop it. Okay? Any remaining questions on impulse? Again, feel free to, I want you to shout them out or Even little things I want to clarify as we're going through. We okay with impulse? All right. So reboot this. Homework questions. Let me know who asked me. Aiden, which ones do you want me to talk about? Okay, that's good. We just talked about it. Let's try to work through them together. So on the homework, which page are you on? What, number 1, number 2, number 3?
2.
Number 2.
On H and I couldn't figure it out.
H and I. Okay.
I don't have my paper. You have it.
Oh, good point. I was actually meaning to. I wanted to get those back to you. For those of you that already turned it in. Oh, I set it up. I forgot it. Here, buddy. Okay, I want to make sure I graded all of them. So they should be in Power School. If I grade them, they're in Power School. Okay? So that brings me up to a side point, right? We got our test for Unit 5 on momentum next class. What is also due next class? Bingo. Anything for Unit 5 needs to be turned in to me next class. Alright? When we take that test, our unit officially ends, so all your homeworks, all your lab, right? The collision. Some of you guys are missing that collision assignment on Google Classroom. Right? So I really need you guys to, for your own sake, go to Power School. If you got a 0, like, hey, I either didn't do it or let me know. Like, hey, Mr. H, I turned this in. Then you go to Classroom. Right? The PhET simulation's on Classroom. If you're missing homework 2, this worksheet, you either need to bring it back to me by next class. When you walk into my room for this test, that's when it's due. If you want to turn it in tonight, I mean, you could throw it on Classroom. Just take a picture and submit it. I can get that. That works. You can give it to me ish today. You can turn it in tomorrow during the passing period. But please don't. I don't want to see anybody have any 0s for homework because you just forgot something, right? You've had a lot of time. I'm telling you, coming down to it, just get it turned in. This will help you on the test. Anyway, getting back to Aiden's question. On the homework, page number 2, H and I. Yeah. So H and I, those questions we're asking, it told you, hey, for H, delta T equals 0.015 seconds. The time for the collision was 0.015. Again, here, what is the average impulsive force? All that means is find the F value in the impulse equation. F, it's actually AVG, is unknown. This is important to read the question very carefully. This says exerted by cart number 1 on cart 2. That tells you we are interested in cart 2. We want to know what happens to cart number 2. Okay? So first of all, we want to find the force. Well, we need the impulse is F times delta T. I want to find that. I don't know the impulse. That's a problem. I got 2 unknowns. I can't solve for what I'm asked to find. Somehow, I need to find the impulse. Is there a way that I can find the impulse for cart number 2?
You've got to use that long equation, don't you?
Not quite. This one's easier than you probably are thinking. What is the impulse equal to? Ft, of course. What? It's also equal to the change in momentum. Do I know the change in momentum for cart 2? I do. I answered that in the previous questions. So I need to find delta P What was the final momentum for cart number 2? That happened to be question G. What'd you get?
9.9.
I didn't get that.
I got 17.4.
I got 17.4. Did everybody else get 17.4? Because you should have found that the final velocity, part E, in cart number 2 was 14.5. That one would have been tricky because to find the velocity, you need that real long equation. That's the questions that I said, hey, these get really gnarly.
I thought you said that was on the other page.
No, page 2. D and E on page number 2 are where you have to have 2 equations and you have to solve them simultaneously. Aiden?
Can we go over D and E?
You asked another question, dang it, you broke it.
Yeah, we can. Let me finish this.
That could get rid of our. That we could do that for our elastic collision. Talk about elastic collision for a bit.
Okay. Yeah, I'll finish this question and I'll circle back for elastic. Okay, so right here, Trevor had said, hey, impulse is also equal to the change in momentum, and I know that. Question G asked you to find the final momentum of cart 2. Well, the final was 17.4. That's final. I need to subtract the initial. Well, the initial is in question B. What was the initial momentum of cart 2? It's 2.4. Now, I have an equation with one unknown. I just do algebra, solve for F. Alright, subtract these two, divide by 0.015. What did you guys get for the force? Yeah. Positive or negative? Positive. Final minus initial gave us a positive. Your time has to be positive. A negative time doesn't make sense. So your force is positive 1,000 newtons. Did you notice this was double the force of the same initial scenario as question 1? Question 1 was inelastic. Question 2 was an elastic. Can anybody explain to me why the force was double during an elastic collision versus an inelastic? John?
Because in elastic collisions, you conserve both momentum and kinetic energy.
That's true. Elastic, you conserve both kinetic energy and momentum. That is true. But why does it take more force in an elastic collision? Again, all the masses, the velocities, they're the same. It's just the type of collision changes.
Because in an elastic collision, they start going this way, they stop, and then they go this way.
Yes.
In an inelastic collision, they hit, and they just go.
Yes. In an inelastic collision, they come together and they link up, and then whoever wins, that's the way they go. So all you're really doing is stopping the other cart, and then the leftover momentum moves it. In an elastic collision, they not only come together, collide, and stop, but they also get repelled the other way. That's a lot harder to do. It's harder for me to stop something and push it back than just stopping it. That's really what's happening. That's why you see a double the force for the elastic collision for the same initial setup as you did for the first problem, which was an inelastic collision. Does that make sense? Inelastic, you're just stopping and then the leftover momentum moves you. Elastic means they stop and bounce off. That's harder to do. That's why you have more force. And then H, the second question, HI. Wait a minute. I wrote this wrong. This was G. Your question wanted G and H, right?
I wanted H and I.
You wanted H and I? So this, I technically did G. That was my bad. I or H would be the same thing but opposite. The same thing but cart 1. So cart 1, I would do same time. It's the same two carts colliding together. Delta T is the same. I want to find the average force. Well, I'm going to do the same process. Force times time is my change in momentum. Cart number 1, what's the final momentum? That was question E, or 16.5. Did everybody get that? Question E. Hopefully. Okay. I mean, all these questions rely on each other. So if you made a mistake early on,
you said E was 16.5?
E was the final momentum of cart 1, which I put in for
No.
D.
E is the final velocity of cart 2.
F is the final momentum.
Oh, I'm on page 1.
Yeah. Because I say E is 14.5.
Because you originally had those right, like the G and H. Because the top one's H.
Yes.
No, I'm talking about where you have G on the board. Yep. Yep, and that one's I.
This was H. Yeah, so I was answering your right questions. I was looking at the wrong page. I was reading question 1. Sorry. So Aiden, I was still answering your questions for H and I. H we did correctly, 1,000 newtons.
Yeah.
Right? It was on cart 2. Now we're doing question I on page number 2, which is on cart 1. So same sort of process. What's the final momentum of cart 1? That was question F9. I got to do final momentum minus initial. What was my initial momentum? All the way on question A, 24. This is a good example to show you guys. What's 9 minus 24? And now I divide out 0.015, gives me the force. Negative 1,000 newtons.
Wow.
It's a negative. Right? Your math tells you that, so you're good. But it's a negative force. It should make sense when you think about cart 1 is moving this way. Cart 2 is also moving this way, but a lot slower, right? Right? This guy's hauling, and he's going to rear end that cart. They're going to bounce off each other. What's going to happen to this cart? After this guy runs into his rear end, yeah, he's going to be launched forward. So what direction is the force on cart 2 going? This way. On cart number 2 was 1,000 Newton force in the positive direction. That makes sense. What happens when this cart rear ends this guy? What happens to this?
You can see a negative 1,000 because it's hitting it and bouncing back.
Yeah, it's colliding, and that car in front of it is pushing back on it. Right? The impulse, again, they're equal and opposite because it's the same collision. Right? The total momentum is conserved because this was my system. Nothing's coming in or out of the system. It's all happening inside the system. So the total momentum doesn't change. That gets to our, well, we don't have it, but conservation momentum. Should make sense in the same collision. Cart 1 is going to push cart 2 forward. Cart 2 pushes back. It's equal and opposite. You can see that in their momentums. So that's H and I. So you want to circle back and do D and E. Okay, this one, again, I told you the algebra is gnarly. Yeah, it's first time turning on today.
Oh, I thought that was your computer for a second.
No.
When I first turned on.
Yeah, that'd be bad news.
And I was a little concerned.
Okay, so you guys see this? D and E is tricky. No, not concept, algebra. D and E was saying, hey, find the final velocity. Well, John, like you said earlier, he noticed this was an elastic collision. So you conserve kinetic energy and momentum. Right? Now, normally, you would have to do, right, to get D and E, to solve these two, you would have to say, P1 initial plus P2 initial is the same as P1 final plus P2 final. Right? You would also have to do KE kinetic energy, 1 initial plus KE 2 initial is the same thing as KE1 final plus KE2 final. Those are two conservation equations that you get to apply to this problem because it's an elastic collision. Right? So you'd say, okay, mass velocity initially for cart 1, mass velocity finally or initially for cart 2. You would know those, right? This was given in the problem. This was given in the problem. However, you don't know these two, at least individually. Because to get the final momentum for cart 1, you need cart 1's mass and cart 1's velocity. Right? That's what D and E are trying to find. So we don't know those two. So I can't solve this problem. I got to use another equation right here. 1/2 mv squared. I know that. I know mass and velocity, mass and velocity. I don't know these. I know the masses, but I don't know the velocity. I got a bunch of unknowns. How you do this, the original or full way, is mv, 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 mv. Plug in what you know here. Then you'd have an equation with two unknowns, V1 final, V2 final. So what you're trying to find for questions D and E. Then you would say 1/2 mv squared, 1/2 mv squared. You plug in what you know. You can get a number over here, but it's equal to 1/2 m, an unknown v squared. 1/2 m, unknown v squared. So now you have two equations with two unknowns. You can solve it, but you have to combine the two equations. Have you guys done this before in Algebra 2, calculus? I'm sure you've done it sometimes, right? You solve a system of equations. You have two equations and two unknowns. V1 final, V2 final, pops up in both of them. You got to solve one equation for, say, V1 final. It equals a bunch of stuff. Plug that in here. So all you have is V2 final, combine everything and simplify. It's not difficult, it's just a lot of algebra. This gets really messy, because you got 1/2 mv squared. Now you're dealing with a variable squared. You're going to have to do the quadratic formula most likely. There's two solutions to a quadratic equation. When you do this, you would get, say, like 5 and negative 0.3. In your head, you'd realize, wait a minute, part 2 ends up going in the positive direction. I know it can't be negative, so I eliminate that. There's your answer. You plug it in and solve for the other variable. There's your two answers. They gave you a hint in the top right, there is a equation for just the velocities that instead of doing this, your second equation would be V2 final minus V1 final is V1 initial minus V2 initial. Right? I know all the initial velocities. I don't know these two. That's the same variables up here. Two equations, two unknowns. I would say do, right, solve this V2F. If I add this over here, you see that? Just take algebra and move this over. I have one equation just solved for V2F. That would get plugged in right here. Then, this whole equation, the only variable missing is V1F. V1F, I'd combine them and solve. That would give me V1F here. I could take V1F and just plug it back into this, solve for V2F. That would give me E. I don't want to do the algebra. It's a lot of tedious algebra. I don't really care so much about the algebra. Do you get the process of how I got there? I want to review. First of all, you'd think, okay, I know conservation of momentum. Crap, I got two variables. I can't solve it. I need another equation. Oh, it's elastic. I conserve kinetic energy. Now, you could do this. That's the right process, and then you just got some gnarly algebra. But this homework gave you a key equation in the top right for elastic collisions only. I plug that in and then just solve two systems of equations. So after you get these two, it's just algebra. So that's your answer. It's probably not an answer you like, but as long as the process makes sense, that's important. That you acknowledge, okay, elastic collision. I conserve momentum. That's easy. It's an elastic collision, so I also have to conserve kinetic energy. Wait a minute, the problem gave me a key equation. I'm going to use that instead. That's way simpler. Then you got two systems of equations to do algebra. Okay? Again, I know you probably don't like that answer, but I don't want to spend time showing you algebra. I want you to show you how to set this up and then say, hey, you would do algebra, solve for this variable, plug it in, get the actual value for V1F. Got question one done. Plug it in. I know this, I know this, I know this now. Solve for the unknowns. That's question two. And then you can keep moving from the rest of these questions. Okay? So another point, Ethan, you were talking about collisions. Biggest thing to remember, in an elastic collision, you conserve momentum, just like you do in any system of equation, or system that involves a collision. You're going to conserve your momentum, whether it's elastic or inelastic. You always conserve momentum in a collision. However, an elastic collision has the added benefit of you conserve kinetic energy. You conserve kinetic energy only in elastic collisions, not inelastic. All right? Did you have something more specific that I can touch on for elastic collisions? Or what do you want me to zoom in on? Like, how can I best help?
I think I'm good.
That makes more sense? Do we feel all right for collisions? You're going to be given two objects. You'll probably get the mass of both, maybe even the velocity of both. Asks you for initial momentum or final momentum, right? You use your conservation of momentum. Sometimes it might give you masses of both carts, but only the velocity of one cart. It'll tell you the final momentum, and you got to take the final and work backwards to figure out, hey, what was the initial velocity of this cart over here? If I know the two added together equals this, I got to solve that missing piece. Or they might tell you the impulse. You got to find the change of momentum, use the change of momentum to get the original momentum. All right? So in any sort of collision, this is your golden equation. You know conservation of momentum. Both your objects initially have a certain amount of momentum. That total momentum is the same at the end. So P1 final, P2 final. Basically, they're going to leave something missing, and you got to find that missing piece with that equation. Okay? Anything else for collisions? Yes, Ethan.
What is the answer for D? Just like
D on question number 2,
yeah.
I got 4.5 meters per second.
Okay.
For cart number 1, which is question D. Question E, if you plugged 4.5 in for velocity 1, you would get 14.5
Gotcha.
for cart number 2. And it should make sense, right? Because cart 1 is coming in hot. Cart 2 is just tinkering along. They're going to collide elastically. This guy's going to get ricocheted ahead. So it makes sense that cart number 2 has a huge final velocity. It gets launched forward 14.5.
Right.
Makes sense that cart 1, that velocity tanks. It originally was 12. Once it hits this cart pushes back, slows it down. All the momentum here is transferred. So this guy loses momentum. So his final velocity was, 4.5 rather than its initial of 12. That makes sense. It's a gut check you could do to make sure you didn't flip V2 final and V1 final.
Mm-hmm.
Right? It wouldn't make sense if cart number 2 got hit from behind and yet somehow went slower than it was originally. You would think, that doesn't make any sense. That wouldn't happen if this situation occurred. So you can gut check yourself. You might have flipped your variable numberings or whatever. Anything else with collisions? Okay. Homework? Any other remaining homework questions? That leaves us, I guess, question number 3 is very similar to this idea of, hey, what about these pendulum bob thingies? So I want to talk about this because this is a really unique momentum problem that they really like to throw out because it's a really good test of, do you understand what the system is and what's happening? You have a block that's hanging and a bullet's coming in. I don't know how to draw this. You got a bullet that's fired at a wooden block hanging, right? Does everyone get that's what the setup is? You got a bullet shot at a wooden block hanging on a pendulum string. They collide. Is this an elastic collision or an inelastic collision? Are you sure?
Inelastic.
What do we think?
We're assuming that the object, the bullet stays in it, so they're becoming like one object.
That's true, right? The bullet gets lodged in the pendulum.
Wait, yeah, I was thinking that.
Okay, that's good. This is why really slow down. And okay, elastic collisions, they bounce off of each other. That's not happening here. They're getting lodged together. That's inelastic. They stick together. This bullet gets trapped inside. This bullet is now inside the block, and it swings forward. So it goes, right? It swings up, which makes sense. Right? If I shoot a bullet at a hanging block, the bullet's going to push that block up until it comes back down. Right? So we have a couple things. This is a unique thing. right? That's different than an inelastic collision. This says that in this scenario, the mechanical energy is conserved, right? The problem specifies that, so you can be like, okay, this is an inelastic collision, but it told me, hey, for this scenario, you do conserve the mechanical energy, right? So there's a lot of questions that they asked about it. One of them is, what's the final potential energy of the bullet bob system? Well, the question actually told you. Here's how high it gets. Right? The height from start to finish was h. You guys remember how to find the potential energy of an object? mgh. H, it told us. G, we know. What is m? What is the mass of the system as it swings to its peak? Maggie said you add them. Not one. That would be just the block. But the bullet gets lodged in the block. Now you have a block and bullet combined. So that is the new mass.
So would it be 0.005?
Plus 1. Yes. The total mass is 1 plus 0.005. That's because they get stuck in each other. They're connected. They're now joined together. That's a common thing that some people will miss. Final kinetic energy. Well, what happens when it reaches its maximum height? Is it moving? No. That's why it's at the maximum height. It gets hit, and it swings out until it stops. So KE is 0. You could plug in 1/2 mv squared and then say, oh, velocity is 0, so its total is 0. Again, that's at the end when it swings out max. You guys see those two? Well, then it's saying, what was the initial potential energy? It's kind of weird. What was the potential energy at this situation? Yeah, they're both at height h equals 0. At least you assume that. Right? So this would be 0. So that means all the energy that this block ended with, it was potential energy, no kinetic. Where did that energy come from? It certainly didn't come from initial potential energy. So where did it get this energy? There's 3 options. It could have gotten it from gravitational potential energy, could have gotten it from kinetic energy, could have gotten it from potential spring energy. We just said it was 0 though, because we said it started at ground level.
Yeah.
So where did it come from a spring? No. We just said that there's no gravitational potential. What's left? The kinetic energy.
Okay.
Right? The collision put energy into this block bullet system. That is the energy that it starts with, which happens to be the same thing as the potential energy it ends with. Because for this inelastic collision, you would have said, oh, kinetic energy is not conserved. But actually, it's telling you the mechanical energy is conserved. So that's where this part D, would say, what's the initial kinetic? Well, you know it. It's the same number you got for question A, the final potential energy. Number from A. I think I got 1.18. That was my initial potential. There's no kinetic for part B. Part C, what was the initial potential? Well, it was 0. Is that height h equals 0? What's the question D? What's the initial kinetic? Wait a minute, mechanical energy was conserved. So if I ended with 1.18 joules of potential energy at the very end, I had to have that much kinetic energy to start with. So that's what D is, 1.18. Then you keep going and say, oh crap, E, what's the initial velocity? Well, shoot. I know that KE equals 1.18, and this equals 1/2 m. What is the mass of the bullet bob system? Say it again. That's the bullet.
Well, we did this in class.
Yes.
And you had us just do the bullet system.
Yeah, this is where I don't like how this question is set up.
That's why we didn't do H. H was not so.
Actually, I redid this. I forgot about that. I redid this problem after we had such a mess. I rethought it. So I figured out we should have actually still done the bullet bob. So you would have done 1 plus 0.05. The mass of the bullet bob system, again, if you have this, don't change it unless you really want to. If you turn this in, I'm going to give you points. I want to just clarify. This was the energy of the bullet bob system right when it started to move. Well, I know the mass of that. It's the bullet plus the block. And then the velocity is unknown. Well, that's a simple algebra equation. This turns out to be, whoops. I think it's dry erase. Sorry, janitors. Drawing all over their floor. No, stop. 1.53. That was the initial velocity of the bullet and block immediately after they collided and started to move. Very, very beginning. That total amount of energy gets transferred into potential energy when it eventually stops. All the kinetic energy it begins with, right after the collision, goes to, basically push it up to a certain height. Okay? Then it switches and said, hey, while the collision is happening, momentum's conserved. So it says, what's the final momentum of the system? Immediately before it starts to move upward. That's this point. This very, very small instant after the collision finishes, but just before it starts to actually move up. That's the initial momentum. Or wait, it calls it final. Right? So then you would say, okay, momentum momentum. What's my equation for momentum? Tell me. Thank you. We should know that. It's of the system. Right? So my mass, right before it starts to swing upward, the collisions happen. The bullet bob are stuck together, so my mass is both of them combined. What's the velocity of both of them? Well, we just found that in question E. That was the velocity, like the moment after the collision happens. Before that, combined system begins to move, it has a certain initial velocity. It was 1.53. Well, that's easy. Doesn't change it much. Kilogram meter per second. Those are my units. Then it's saying, what was the initial momentum of the bullet? Well, first of all, what's the initial momentum of the block before the collision? Should be easy. 0. Why?
Because it was just resting.
It's just hanging there. There's no velocity. Boom. Well, momentum was conserved. How did I have this much momentum after the collision? Where did that momentum come from? It certainly didn't come from the block. came from the bullet. What was the value of the momentum of that bullet before it hit the block? You don't even have to do math. You know conservation of momentum. The momentum of a bullet and a block initially is the same thing as the bullet and the block after the collision. Well, we just found the bullet block momentum after the collision. Mass times velocity, 1.54. If the block had no momentum initially, all of the momentum had to come from just the bullet. So that's just a conservation, right? That's easy. You guys see how I got that? Momentum final equals momentum initial. The block was 0, so that doesn't have a part in it. All of it came from the initial momentum of the bullet. So that's question G. Then, this is where this is what I had mixed up in my head and told you guys wrong. This is the way that it was meant to be solved. Because it makes sense when you get to here. What was the initial velocity? The velocity that that bullet was fired at before it hit the collision? Well, momentum is mass times velocity. I know the momentum of the bullet initially. I certainly know the mass of it. The problem tells me. Simple algebra. What's that come out to? Here's what I got. 308.3 meters per second. That thing's moving. I have no idea what that'd be in miles per hour. $689 mile an hour. Yeah, light work. Speed of sound in miles per hour. Does anybody know that off the top of their head?
Like 2,000.
767. Did I lose my cap somewhere?
It's right by that chair's leg.
Oh, there it is. Thank you. So that bullet is sort of close to the speed of sound. It's moving pretty good. All right? But I want you to see
Not as fast as me.
huge velocity, really tiny mass. You get a certain amount of momentum. That momentum is conserved even after it hits a block of wood. The block of wood is, good grief, like 1,000 times more massive. I don't know the math off the top of my head. Right? 0.005 kilograms compared to 1 kilogram. Makes sense that the actual velocity, 1.53 after the collision, makes sense why that velocity tanked. You have a certain amount of momentum, little mass, big velocity. That total amount has to be the same after the collision, where you have huge mass. So you have to have a little velocity so that it equals the same as what it started with. I apologize that I was confused when we went over this in class. I remember later that day, like, it was bothering me, so I went and redid it, thought through it, and this is the way I should have done it. Does that make sense? You should see the conservation of momentum isn't always like, oh, the velocity is high, so it has to end high. No. You have a tiny mass, giant velocity. Okay, you get some momentum. If it gets attached to a huge momentum or mass, your velocity is going to tank. Momentum is still conserved, but you have a trade-off. You trade a lot of velocity with a little mass for the opposite. A lot of mass with a little velocity. The effect is the same. Right? Okay, any questions? That was finishing up the homework and talking about that pendulum bob type of question. Right? Does that make a lot more sense? Kind of at least seeing it one more time. Seeing that, okay, it's an inelastic collision, right? I can do those. They stick together. Momentum's still conserved. This one said, hey, after it starts swinging, your energy is conserved. Okay, that I need to use. But until then, just use your conservation. Right, set up your equations. This was meant, in some situations, like this question, the page number 3, this might drive you crazy, but a question might give you this setup and then ask you this. They want you to find the velocity of the bullet. You'd have to do all of this stuff because you only know the first step and you can get at. Then you can do the next step. Then it lets you do the next step until you can get this step. But tricky questions are going to give you the info, a little bit of info, not a lot, and ask you this. You can't just throw it in one equation to be done. They're going to make you work for it in certain problems. Right? There's going to be a lot missing that you got to fill in step by step to get to where they're wanting. And in those situations, that question might be worth a lot. Right? If this was an FRQ, they might ask you this and just give you a whole blank page to find this. And when they grade it, they would say, did they use conservation of energy? Yes, they did. You get a point. Did they use conservation of momentum? Yep, they did. You guys get a point. Right? Did they conserve mechanical energy after the collision? Yep, point. Did they get the right answer? Point. Even if you don't know this, throw conservation of momentum down. Just write it. You know it's true, so put it down. Write the conservation of energy equation. You can get 2 out of the 4 points even without doing anything, really. That's part of the strategy we'll talk about when we kind of look towards the actual AP test. Because sometimes it's not about knowing everything. If you did, you're going to get a 5, right? You're that top tier of all the students taking this. That's not the expectation for all of you. You can't all expect to be 5 students. Right? I want you to shoot for that, but you can't expect to be able to go through the problems and get everything correct on time and get all the points. Sometimes you have to realize, like, oh my gosh, I'm stuck. I need to throw some equations down and move on because I'm wasting my time. We'll talk about some strategy like that. Any other questions about momentum? About the pendulum? Can I explain anything else? Right? What's an open system? Yep, energy can come in and out. Mass can come in and out. And forces can come in and out. Right? Some force could come from outside and apply to your system. That would change your momentum and change your energy. What happens if you have a closed system? Yeah, the extreme example is isolated, where absolutely no mass can come in and out and absolutely no forces come in and out. Now, we don't have truly isolated systems in the world, right? There's no way I can prevent air drag from applying to motion, right? You'd have to create a vacuum to do that. There's no way you can eliminate friction, right? There's no frictionless surfaces in the world. So even if I roll a cart in the vacuum, friction still acts outward onto my system. It's not truly isolated. But a closed system...
Infinite energy.
Huh?
I said if we could do that, infinite energy.
Yeah.
Instead of using to get some Vaseline, dump it in the hallway.
That's not frictionless. That's low friction.
It's pretty darn close.
It's close, yeah. Okay.
Vaseline on ice.
That'd be pretty low friction. Well...
No, I feel like the Vaseline would... What would it do on the ice? Would it freeze?
Yeah, that would be tricky, right? If you got Vaseline, it's like a jelly, right? It would start to freeze up and get stiff on the cold ice.
We'll put Vaseline on it and then we'll put
Ice.
It doesn't completely, but it gets more thick,
I know
right?
diesel does, but gasoline doesn't freeze. It just stays.
No, I'm pretty sure it would freeze. It's very, very low. You would need like negative something.
Okay.
But everything has a freezing point. So that would, again, physics, real life is very complicated, right? You got to consider a lot of stuff if you're doing, actual physics. Like an oil, like a true liquid oil, that would be better, right? The effect wouldn't be as bad. Yep.
Temperature, alcohol, it's very, very, very.
Yeah, like gasoline, there's alcohol in gasoline. Alcohols do not freeze well.
Yeah.
Like isopropyl alcohol, like rubbing alcohol, I don't even know if you can freeze it. At least with conventional. Like you can't throw it in a freezer. You'd need like a lab grade deep freeze.
Negative 173.5
Fahrenheit
is the.
Yeah.
No, wait. Yeah. That's
Negative 173.
0.5.
Yeah, that
is the freezing point for ethanol.
Yeah, you're not gonna freeze gasoline, right?
What's Sub-Zero?
Wait. A second.
Negative.
No, this is giving me the wrong thing.
What Sub-Zero? What?
Then it says.
Isn't Sub-Zero just like a temperature?
Sub-Zero. I think that'd be Sub-Zero of 0 degrees Celsius, which is negative 32 or no 32 Fahrenheit.
It says
The freezing point.
It says freezing point for pure alcohol is negative 173 or something.
Yeah.
Fahrenheit, or 114 Celsius.
Yeah. But anyway. Any other questions before I want to talk about the big ideas and then see where we're at. Well, I'm going to review a lot of what we just talked about. Again, I want to point you to where I'm finding this from. That's right. So I'm going to your classroom, and then it's at the very bottom in kind of these general info. This is where I'm finding this document. I really want you to know where this is because it summarizes these key concepts for each unit. It breaks it down by unit, right? It's a good crash course review of, like, what the heck did we need to know for this unit? I should probably look at this list to find out. So I want to talk about these. Oh, you can't see it very well. Okay? Is that a little more visible?
Yep.
First thing,
In theory.
momentum. Some people commonly refer to inertia in motion. That's a good way to think about what momentum is. Remember, inertia. Does anybody remember what inertia was? The concept of inertia. How would you define it? How would you describe it to, a middle schooler that says, hey, you're in AP Physics, you're smart. What is inertia? I've heard that word.
I would say that's your first mistake.
Yeah, first mistake.
But you know it, right? They know you've learned inertia. They know you know the answer. How would you define it to a middle schooler? This is a good test of if you really know it, can you simplify it down so that someone else can understand it?
An object in motion.
Good. Josh just said inertia is a property of matter. Now you're quoting Bill Nye, but that's a key aspect of inertia.
Of course.
Anything with mass has inertia. John, what were you saying?
An object in motion wants to stay in motion.
Yes, that's also true about inertia, right? That's why if I play Red Rover, I don't want to send Brody over. If he runs at the same speed as everybody else, he's got a lot more mass.
Unless you have, like,
I don't want to try to stop that. Inertia, if you have motion, it's going to stay in motion unless something tries to stop it. Inertia, the concept is like a resistance to a change in motion. So if something has inertia and it's in motion, it's going to stay there unless something acts on it. And it's going to fight it, basically. If an object is stationary, it has no motion, it's not going to want to do anything unless something kicks it or pushes it. Momentum is what happens after it gets going. Right? If you got some mass, inertia, and you give it a velocity, that's what momentum is. Mass times velocity. So people use that phrase, inertia in motion.
I didn't think I got to tell the Red Rover story. Last time we talked about.
You didn't what?
I have a story about Red Rover.
Okay. Momentum, we have an equation for it. What is it? Come on. What is momentum equal to? MV, mass times velocity. Good. That should be really basic, right? I want that on the top of your tongue, or tip of your tongue, so that, like, you don't even have to look it up. You know that. Now, however, it is on your equation sheet. It's right in near the top. It's like the top third on the left. P is mv. Okay, so we have our equation. Units. Kilogram meter per second. Right? You literally look at mass as kilogram, velocity is meter per second. Well, duh, that's easy. Kilogram meter per second. Then we got to the impulse. The impulse is equal to the force times the time. That's where you apply a force for a certain length of time. That is what an impulse is. An impulse causes a change in momentum. Note, I did not say it causes momentum. It causes a change in momentum. You could be giving an object at rest. You could be giving it momentum through an impulse. An object already in motion, I could add an impulse and it would increase the momentum. If an object's coming at me, I could apply an impulse and decrease the momentum. Slow it down. In every situation, I'm changing the momentum. I'm trying to, beat a dead horse here. An impulse changes momentum. It's not equal to momentum. So delta P is J or F delta T. Okay? Impulses, you could measure in Newton seconds. That's the direct units. Literally, newtons times seconds. But you also know that's exactly the same unit as a kilogram meter per second. Right? So, if impulse causes a change in momentum, this example says, hey, you got an impulse of 20 newton seconds. Guess what? That causes a change of momentum of 20 newton seconds, or 20 kilogram meter per second. Somehow, whatever's going on here, you increase the momentum by the impulse of 20 kilogram meter per second. Okay, you change the momentum. It's a positive number, so the change was positive. This is a key. We've talked about this a couple times, the elastic versus inelastic. When an object bounces, that's a higher or larger impulse than if it just hit it and stopped. The reason is, it's a lot easier to just take something with a certain velocity or momentum and stop it than it would be to not only stop that object, but then recoil it back the other direction. So in every time you have a bounce, you have a lot higher impulse than if that same situation were redone with just a collision and stop. Right? Momentum is a vector. Right? If I have a certain mass velocity coming in, I could go to 0. That takes a certain amount of impulse. But if I take that vector and decrease it and throw it the other way, I need more impulse. Area under the velocity or force time graph. If I give you the force applied on an object for a given amount of time, and I told you to calculate the impulse from time 1 second to 5 seconds, all you'd need to do is take delta T times F. That's literally the equation for impulse. So in that situation, you're not necessarily using an equation. You're using the area of a graph, which is the same exact thing. Okay? Conservation of momentum. Momentum before is equal to momentum after. However you define your system, whether it's elastic or inelastic collision, the momentum initially of your system is the same as the final momentum of your system, assuming you don't have any mass transfer or any forces acting on the system. Right? Your momentum isn't conserved if some outside force is applied on your system. That should make sense, right? Something is coming from the outside and changing the momentum. Well, duh, it's not going to be the same as when it started, because something came in and changed it. If that doesn't happen, everything happens within your system boundary, nothing's going to change. It's all coming from within the same place. So that's your conservation of momentum. Hold on, make sure when I'm done, you can turn that in. Inelastic collisions. That's when things stick together, right? Momentum's conserved. So you could write your equation and be like, okay, MV1, MV2 initially. But wait a minute, afterwards, they got stuck together. They're now a new combined object. Okay, they got a certain velocity, yeah, but they have a new mass, M1 plus M2. They got joined together. Their masses are added together, and then they have a single velocity because they're moving together. That's inelastic, sticking together. Again, like we had talked about multiple times, do you conserve momentum in inelastic collisions? Yes or no? Yes. You always conserve momentum in the collisions. Right? However, for inelastic, do you conserve energy?
No.
Specifically kinetic energy? No. When objects stick together in the collision, that's inelastic. You do not conserve kinetic energy. You only conserve momentum. Again, they explain it takes work to hold things together. That work has to come from somewhere, right? Friction. That's now an outside force, so you're ruining your conservation of energy. Okay? How about elastic collisions? Do you conserve momentum? Right away, you should say yes. You shouldn't care what type of collision it is. You always conserve momentum in a collision. Do you conserve kinetic energy in an elastic collision?
Yes.
Yeah, that's the nice scenario, right? You conserve momentum and kinetic energy. You can use those to your advantage in those elastic collision questions. That's when they bounce off each other. That's why an elastic. I always think of bouncy balls. Whenever a bouncy ball hits something, it bounces off. Bouncy balls are really elastic. Therefore, elastic collisions, that's how I remember that they always bounce. And I remember, okay, I conserve momentum, duh, and also kinetic energy. This is a unique scenario. If you have an elastic collision in one dimension, right? Holy smokes. That went way faster than I thought. I want you to read through the rest of this, but that scenario, if they have the same mass, elastic collision in one dimension, they literally switch velocities. I want you to keep reading through this, right? If you got your homework, I want you to turn that into me on your way out. Sorry, I lost track of time. I sort of got through everything, but just review that last document. Thank you guys. Study your notes. I'll post an answer key for this assignment. That'll help you study. And then you got your notes, these class recordings, and that big idea document. And then we'll get that test on Wednesday.
I need to finish that last one.
Oh, the FET?
Yeah.
Okay.
Yes, I had some questions about that. I was going to go down and tell my S teacher.
Oh, yes, that's fine. Perfect. Thank you. Hold on, Maggie. Thank you.
Thank you.
Oh, boy. That got away from me.
Mr. H,
Yes, sir.
I have a test to take in Miss Kellogg's to finish.
Okay. Do you have a pass from her, or did you shoot me an email?
No, I just informed her because the test is for Miss Quillen, but Miss Quillen wants me to take it with Miss Kellogg.
Oh, because is Quillen, is she quarantined?
Yeah.
I think she's not here.
Yeah. I talked to her
So,
Friday last night.
Who are you going to? Miss
Kellogg,
and she's basically like proctor while you take it. That's fine. Just give me a second. I'll do attendance. We have one activity, so it'll be like 10 minutes, and then I'll send it down. But that's no problem. Just remind me when I'm done with everything. Remind me again. I'll let you go.
Okay.
You got pass? Okay. Okay. We have. That's no problem. We have one activity that we got to do together. It'll be like 10 minutes, and then bring that up to me. I'll sign it, and then we'll be good to go. Yeah, that's no problem. Are you glad to be back? No. No? What was your school harder on quarantine? Okay, well that's good. Usually I hear the opposite. Well, my students, they don't do anything.
Yeah,
They what?
she said I attended the annual and tried to be for
Yes. I'm used to, if one of my kids goes on quarantine, I can just anticipate, yep, they're not going to do anything for 2 weeks.
Because I was babysitting them.
And you still got it done.
Yeah.
Well, kudos to you, because that's very
3
atypical.
NWE tests.
That's all. I'm glad you did, because they've been asking us to get those done. Thank you for getting those done.
Some of them I missed the first time, but
Poor Mrs. Resch has been stressing. She's kind of in charge of getting everybody to get those done. So she's dealing with all these kids that just don't listen and never get done, and it makes her life difficult. So I'm glad you got it done.
It just said tall. It just about fell.
no, it's part that way. But his hair's much thinner on this side. It looks more like down.
Oh, I forgot this. Darn it.